When dealing with grounding subpanels, particularly 200 amp panels fed from a 600 amp main, several approaches can be taken to ensure compliance with the National Electrical Code, or NEC, and to maintain a safe electrical system. The NEC outlines two primary methods for grounding subpanels. Firstly, directly to the grounding electrode system, which involves running a separate grounding conductor from the subpanel to a grounding electrode, like a ground rod or a water pipe, and secondly, through a grounding electrode conductor, or GEC, within the feeder, meaning that if the feeder from the main distribution panel to the subpanel includes a GEC, the subpanel is grounded through that feeder, with the GEC sized appropriately for the feeder conductor's ampacity. Considering a setup where a 600 amp main is connected to grounding electrodes such as a concrete encased electrode, sometimes referred to as a UFA ground, and a ground rod, with a 14-inch by 14-inch trough integrated into the main distribution panel's grounding electrode system, it's important to note that a current transformer, or CT, is not a grounding device itself. Given that the three 200 amp panels are connected to this 14-inch by 14-inch trough, there are a few potential methods for grounding these subpanels. One approach involves running a separate grounding conductor from each 200 amp subpanel to a grounding electrode, such as a ground rod, which is particularly useful if the resistance to ground at the main distribution panel is notably high. Another method relies on ensuring that the feeder from the main distribution panel to each 200 amp subpanel includes a GEC of the correct size, a method deemed acceptable if the resistance to ground at the main distribution panel is low. A third method combines a GEC in the feeder from the main distribution panel to each 200 amp subpanel and uses bonding bushings at the subpanels to connect the subpanel's ground bar to the neutral bar, establishing a comprehensive path for ground fault currents. This method is advisable if the neutral conductor isn't consistently bonded to the grounding system throughout the electrical installation. Based on these considerations, using the third method, combining a GEC in the feeder with bonding bushings, is generally recommended for grounding the 200 amp subpanels. This ensures a robust path for ground fault currents and aligns with NEC requirements. When implementing these grounding methods, it's crucial to understand the roles and requirements for grounding electrode conductors, equipment grounding conductors, and bonding jumpers. The grounding electrode conductor connects the system's grounded conductor, typically the neutral, or the equipment, to a grounding electrode. This electrode could be a ground rod, a ground plate, a metal underground water pipe, or a concrete encased electrode. The size of the GEC is determined by NEC Table 250.66 based on the size of the service entrance conductors. For example, if you have copper service entrance conductors sized at 500 kc mil, the corresponding copper GEC size would be no smaller than 1/0 American wire gauge, or AUG. Equipment grounding conductors, or EGs, on the other hand, provide a low impedance path for fault current to return to the source. They ensure that overcurrent protection devices, such as circuit breakers or fuses, trip quickly in the event of a ground fault, minimizing the risk of electrical shock or fire. EGC can be wires, metallic conduits, or other approved metallic pathways. Their sizing is determined by NEC Table 250.122 based on the rating of the overcurrent protective device in the circuit. For instance, if the overcurrent protection device is rated at 200 amps, the minimum size for a copper EGC would be 6 AWG. Bonding jumpers are used to connect metallic parts of the electrical system to ensure electrical continuity and create a low impedance path for fault current. They are commonly used to bond metallic enclosures such as junction boxes, service panels, and equipment frames. Bonding jumpers are sized according to NEC 250.102, which references Table 250.66 for sizing the bonding jumper for service equipment, and Table 250.122 for equipment bonding jumpers. When installing grounding and bonding systems, several best practices should be followed. Firstly, always refer to the latest edition of the NEC and local electrical codes for specific requirements and interpretations. Secondly, ensure that all grounding and bonding connections are mechanically sound and electrically conductive, using appropriate connectors and methods. Thirdly, use anti-oxidation compounds on aluminum connections to prevent corrosion and maintain conductivity. Fourthly, when running grounding conductors through metallic enclosures, use insulated bushings or fittings to protect the conductor from abrasion. Fifthly, perform regular inspections and testing of grounding and bonding systems to verify their integrity and effectiveness. This includes checking the tightness of connections, measuring ground resistance, and conducting continuity tests. In the scenario described with a 600 amp main feeding 3 200 amp subpanels, the trough plays a critical role in the grounding system. The trough itself must be properly bonded to the grounding electrode system. This is typically achieved by connecting a grounding electrode conductor from the trough to the grounding electrode, such as a ground rod or the building steel. The size of this conductor is determined by NEC Table 250.66 based on the size of the service entrance conductors feeding the 600 amp main. Within the trough, ensure that all metallic components, such as the trough itself, any junction boxes, and the enclosures of the 200 amp subpanels, are properly bonded together. This can be accomplished using bonding jumpers sized according to NEC 250.102. These bonding jumpers create a low impedance path for fault current, ensuring that overcurrent protection devices will trip quickly in the event of a ground fault. From the trough to each 200 amp subpanel, you have the option of running a separate grounding conductor or relying on the metallic conduit as the equipment grounding conductor. If using a separate grounding conductor, size it according to NEC Table 250.122 based on the rating of the overcurrent protective device feeding the subpanel, in this case 200 amps. If relying on the metallic conduit as the EGC, ensure that the conduit is properly installed with tight connections and that any necessary bonding bushings are used to maintain electrical continuity. At each 200 amp subpanel, the grounding conductor or the metallic conduit must be connected to the grounding bar within the subpanel. The grounding bar is then bonded to the subpanel enclosure, ensuring that the enclosure is also grounded. In addition to grounding, bonding is crucial for minimizing voltage differences between metallic parts of the electrical system. Bonding helps to create a low impedance path for fault current, reducing the risk of electrical shock and fire. Common bonding techniques include bonding metallic water pipes, gas pipes, and structural steel to the grounding electrode system. This is typically accomplished by connecting bonding jumpers from these metallic components to the grounding electrode conductor or to the grounding electrode itself. When bonding metallic water pipes, be sure to bond around any insulated couplings or sections of non-metallic pipe. Similarly, when bonding gas pipes, be aware of any local regulations or requirements that may apply. In some cases, it may be necessary to consult with the gas utility company to ensure compliance with their standards. Structural steel can be bonded by connecting bonding jumpers to the steel frame at multiple points. This helps to ensure that the entire steel structure is at the same electrical potential, reducing the risk of voltage differences. When running conductors through metallic enclosures such as conduits or junction boxes, it is important to protect the conductors from abrasion. This can be accomplished by using insulated bushings or fittings at the entrance and exit points of the enclosure. These bushings or fittings provide a smooth, rounded surface that prevents the conductors from rubbing against the sharp edges of the enclosure. In addition to protecting the conductors, insulated bushings and fittings can also help to reduce the risk of ground faults. If a conductor is damaged and comes into contact with the metallic enclosure, a ground fault can occur. By using insulated bushings and fittings, the risk of this type of fault is minimized. Regular inspections and testing of grounding and bonding systems are essential for verifying their integrity and effectiveness. These inspections should include checking the tightness of connections, measuring ground resistance, and conducting continuity tests. Loose connections can increase the impedance of the grounding path, reducing its effectiveness. Use a torque wrench to ensure that all connections are tightened to the manufacturer's specifications. Ground resistance testing measures the resistance of the grounding electrode to the earth. A low ground resistance is essential for providing a low impedance path for fault current. The NEC recommends a ground resistance of 25 ohms or less. If the ground resistance is higher than 25 ohms, additional grounding electrodes may be required. Continuity tests verify that there is a continuous, low impedance path between all metallic parts of the electrical system. Use a multimeter to perform these tests, checking the continuity between the grounding electrode, the grounding conductors, and the metallic enclosures. In summary, grounding the 200 amp subpanels from the 600 amp main involves a comprehensive approach that considers NEC requirements, grounding electrode conductors, equipment grounding conductors, bonding jumpers, and best practices for installation and maintenance. By following these guidelines, you can ensure a safe and effective electrical system. Remember to consult the latest edition of the NEC and local electrical codes for specific requirements and interpretations, and always seek the assistance of a qualified electrician if you are unsure about any aspect of the grounding system. Understanding the purpose and function of each component in the grounding system is critical for ensuring its effectiveness. The grounding electrode system provides a reference point for the electrical system, helping to stabilize voltage and prevent overvoltages. The grounding electrode conductor connects the system's grounded conductor, typically the neutral, to the grounding electrode, providing a path for fault current to return to the source. The equipment grounding conductor provides a low impedance path for fault current to return to the source, ensuring that overcurrent protection devices trip quickly in the event of a ground fault. Bonding jumpers connect metallic parts of the electrical system to ensure electrical continuity and create a low impedance path for fault current. Proper grounding and bonding are essential for protecting people and equipment from electrical shock and fire. A well-designed and properly installed grounding system can significantly reduce the risk of electrical hazards. By following the guidelines outlined in the NEC and local electrical codes, and by seeking the assistance of a qualified electrician when needed, you can ensure that your electrical system is safe and reliable. Furthermore, consider the specific environment in which the electrical system is installed. In corrosive environments, such as coastal areas or industrial facilities, additional precautions may be necessary to protect grounding and bonding components from corrosion. This may include using corrosion-resistant materials such as stainless steel or copper, and applying protective coatings to exposed surfaces. In areas with high soil resistivity, it may be necessary to install additional grounding electrodes or use ground-enhancing materials to reduce the ground resistance. Soil resistivity is a measure of how easily electricity flows through the soil. High soil resistivity can make it difficult to achieve a low ground resistance. Ground-enhancing materials such as bentonite clay or chemical ground rods can be used to improve the conductivity of the soil and reduce the ground resistance. Finally, remember that grounding and bonding are not one-time tasks. Regular inspections and maintenance are essential for ensuring that the grounding system remains effective over time. Schedule periodic inspections to check the tightness of connections, measure ground resistance, and conduct continuity tests. Address any issues promptly to prevent the development of electrical hazards. By taking a proactive approach to grounding and bonding, you can protect your property and the people who use it from the dangers of electricity.